We had that one last.
Yeah.
Anyway, hello, folks. My name is Zdziarski. I am a geologist, actually. I work at New Jersey City University, part of the Earth and Environmental Sciences Department, and also the member and observing chair of the North Jersey Astronomical Group. So this is a interesting way to look at climate change. We're not going to look at climate change in the traditional aspects, but if anyone can hear me out in Zoom land and here, when you hear climate change, what do you usually think about? Yeah, anybody?
Severe weather.
Severe weather, that's a good start. Anyone else?
Warming of the planet.
Warming of the planet.
Sea level.
Sea level rise, yeah. Anybody in Zoom land have when you hear climate change, what do you think of? Anyone?
Temperatures rising.
Temperatures rising. Okay. All these things are true in their own ways. Our planet is warming through mostly from human-caused greenhouse gases in the Earth's atmosphere. And now we're actually starting to see some of the early results of this warming of the planet. So Kevin, would you advance the slide? Thanks. So just a quick recap, it's a very basic greenhouse effect in a nutshell. So you have incoming solar radiation from the sun. It penetrates our atmosphere. Some of it is absorbed by the atmosphere itself. Some of it is absorbed by the ground, the surface of the earth and the ocean. Some of it is reflected back out into space, both by the ground from infrared radiation and from the clouds and whatnot. The other part, what parts of our atmosphere that hold all these greenhouse gases in, hold all the heat in, or at least in this nice balance. Water vapor, methane, and carbon dioxide. Those are the three major players in keeping our greenhouse effect in this equilibrium. Now, move to the next slide. As our CO2 levels rise and we go over 400 parts per million, we're now really starting to see more of this heat being stored and reflected back to the Earth. And so it goes to various places. It goes into the atmosphere, it goes into the oceans, and it goes to other various places. So now that equilibrium is now out of balance, and our planet is now warming. There are consequences to that. Kevin, could you move it again? So how does this affect astronomy? The major thing we're gonna talk about is solar radiation affecting water vapor. That's kind of and the weather system. So here's a very basic model of the water cycle. We're going to talk about a small part of it. When the sun heats the Earth, any water that is in small ponds and that are evaporated out of the ground, trees when they exhale, humans when they exhale, it eventually makes its way up into the atmosphere. Condensation occurs when it cools, and eventually it rains. But as the atmosphere warms, the atmosphere is able to hold more moisture. So with its increasing heat energy and more moisture, we get more clouds. In drier areas that are arid regions, deserts, they are more prone to dry out more. You do get more clouds than you did previously, but you don't get as much rain. Those clouds, however, if you can forward the next slide, do make their way to areas that are prone to more wet weather anyway. I.e., the Northeast United States is a good example, where we live here. So we're already prone to, having this nice temperate, in our area, semi-Mediterranean climate. Now we're adding more heat and moisture, and we're getting more cloudbursts, more rain, and more water vapor in the atmosphere, even on days that are not cloudy. So what does that mean? Send it? We're getting cloudier. This is an old favorite of mine. Matter of fact, this picture is posted in the main lodge of the Adirondack Astronomy Tree. Hey, Kevin, can you move that back over? Yeah, thanks.
That's what I'm coming.
Yeah, so this is called the Optimist, and the guy on the right is saying it'll clear up any minute. And there's many of us, we've done, we've had our outreach events, and we're sitting there looking at small patch of sky and saying, oh, look, it's a sucker hole. But going back and looking at some data, on average, now the way that this data was logged together, if it was partly cloudy on that day, it was logged as partly cloudy and cloudy were logged together. Between 1965 and 1990, every year you got about somewhere between 175 and 200 cloudy to partly cloudy days. And that means there could be clouds at any time. It could be clear later on, but if there was clouds, part of that day was logged as a cloudy or partly cloudy day. 2010 to 2021 is average cloudy and partly cloudy days increased quite a bit from 227 to 307. So we're having much less time available to observe the night sky than we did previously. Kevin, Hugh, just bring it over one more time. Yeah.
Forward?
Oh, yeah, forward. Thank you. So this is, if anyone's familiar with the clear sky chart, this may look a little bit familiar. It's not a very easy to read chart. But you can notice here, just take one takeaway here is your blue colorations are clear skies, gray, dark gray, cloudy and partly cloudy. So particularly you're looking at these, like this is going, this axis, the x-axis is going from January to December overall, right? Y-axis is time of day. So most people are, if you're an average nighttime after dinner astronomer, you're looking between 6 p.m. and maybe 12 a.m. and maybe 1 a.m. So you're looking at that upper chunk over there. And you can see there's chunks of gray and chunks of blue, but the blue is pretty thick and pretty consistent. So we're going to take a sample now from 2021. Move one more slide over. Okay. Thank you. The blue still exists, but notice it's thinner and much more spread out than it was in the slide before. So the number of days that we are getting clear skies, or not for parts of the day, even if you look at it on the y-axis, is getting smaller. It's thinner, it's decreasing. So we have less time to observe. One more slide, please. So what does all this mean? Warming climate, again, is putting more moisture in the atmosphere. Even on clear nights, supposed clear nights, if you have a humid night or a night which is stagnant air, if there's moisture in the atmosphere, it will scatter light, particularly if you're near a place like a city that has light pollution. And so that sky glow that the city produces naturally is enhanced by this light being scattered from small water droplets. And in particular, you can go one more slide. Next. As we are switching to blue LEDs, we call them blue because they look like white blue. So they're called cool white lights, and they tend to go towards the blue part of the spectrum compared to incandescent and sodium vapor lamps. So you have this big spike in the blue, and the spike in the blue happens to be a shorter wavelength and happens to scatter much better with water vapor. So these two things are meeting each other, are changing to blue LED lights to be more efficient. At the same time, we have more moisture in the atmosphere. Can we go one more? Thanks. So if we look at this picture from the top of the Griffith Observatory, this is LA, you can kind of see off to the right, there's a giant spotlight in kind of a blue-white color, and a lot of the lights in the foreground here are on the blue part of the spectrum. They are, if you look at above the city, that sky glow is much brighter than it would be if it were sodium vapor. Now, in the background, there is some sodium vapor, but also that's LA in the background. I'll get into that in a minute, but I'm a small preface to that. It's redder and yellower and redder in color for a reason. There are more particulates in the atmosphere there. There are cars and trucks and things of that nature. So that is causing it to scatter more closer to the red than it would otherwise be to the blue. But overall, this picture is showing more blue scatter. Can we go to the next one? Now here's an old school sodium vapor light. Again, it's another humid night. You know, it's July. You can you look really close. You can see Scorpius over here and Sagittarius. It's nice August, humid August evening. But the sky is still visible. Both nights were technically clear nights, but the sky is more visible with the light that spiked more into the yellow. Next one. So another casualty of climate change is again, we were talking about those arid regions being drier and therefore now more prone to severe forest fires. And it's been in the news for quite a few years now. California, Southwest, Colorado, they've been suffering really badly from these dry conditions. And what does this do? Well, obviously we're seeing a lot of red here, color obviously from the fire, but also from the smoke as well. And that smoke will go somewhere. Kevin, next one. These fires are also affecting large professional observatories. Kitt Peak had some damage in June. And the Large Binocular Telescope in Arizona also had a run-in with a fire as well. Next slide. But what happens to us on the East Coast? What happens to other astronomers across the country that, forest fires are nowhere to be seen? These fires are large enough that the particulates that they throw up into the air get caught by the jet stream. And that jet stream will carry it across the country, carry it aloft until it even reaches our area. Kevin, next one. So this snapshot was actually out of my backyard. It's about a month ago. We had, some particulates in the atmosphere from forest fires in the West that had started in late August. And they made their way here weekend of like 9/18 or 20th, somewhere in there. But the sky turned a reddish color. And why is that? Because the scattering effect, even though the scattering effect with these particulates, they're larger than the water droplets. So it's catching the larger wavelengths from the red part of the spectrum. Get in, next slide. So I just made this thing. So go to the next one, sorry.
Sure.
This is what I was getting at. So you're going to wind up with spectacular sunsets. So your skies are going to be much redder, and even bright objects in the evening. For instance, this was last year, the picture of the moon, also in the middle of the summer. Again, there was another time where there were a lot of forest fires out west. But folks that were imaging planets at that time were having trouble. They couldn't get the colors right, the saturation wasn't right. And so even when I took this picture of the moon, it almost, looks yellow-orange or anything else. So that has an effect on your observing. If you're taking pictures of Jupiter, Saturn, you're not going to get true images. It'll be dimmer. The moon will be distorted. But then when you go to deep sky objects, Kevin, the next one. Deep sky objects, if you're trying to do visual work, looking through an eyepiece, are almost impossible to do. So this was last year. This is Pillars of Creation. These are 2 different nights. I think this might have been with my little C8. I was doing electronic assisted astronomy, EAA. And the night on the left is an example of average transparency. And the one on the right was one where it was after one of these smoke events. I tried to look at the object visually. It was invisible on that night. So depending on how thick the smoke is, you may or may not be able to see galaxies and nebula and dwarf clusters and things of that nature. However, as bad as this image is on the right, if you're using the camera just from a pure observing standpoint, you're able to see the object still. So the takeaway from that piece is, well, perhaps this part that we have to live with climate change, there's still a workaround. And if you're persistent enough, you can still make the workaround work from an observation standpoint. Now, the object won't be as pretty a picture if you're taking a picture, but if you're using it to observe the dust lanes and do public outreach, or if you're doing any kind of science to varying degrees, because if you're looking at spectra, the smoke will definitely mess with that. If you're looking for purely visual aspects, you can still do some work there. Next slide. So the other part of climate change, unfortunately, you're dealing with these more extreme weather events, but it's also doing things to our jet stream. So what we like to see is a nice laminar jet stream that goes straight across, from one side of the country to the other side, right? But when you start seeing these dips and troughs, usually you see more disturbances there. And we go to the next slide. So when the Arctic warms up, the jet stream, the polar jet stream, tends to weaken. And when I say weaken, it actually technically slows down a little bit. It also starts to become wavy. And if you look at this picture on the left, can we put this to the middle? The pictures are in the middle. Yeah, that's good. So if you look at the bottom graphic on the right here, you see the warm air from the tropics moves forward, right? And you have cold air moving southward. So this has an effect of kind of turning the jet stream into a giant sine wave. So you have low pressure that likes to ride along that jet stream. And that hot and cold clashing actually feeds storm systems. Next slide. In the winter, we have a name for it, kind of like it's called the polar vortex. There is another name, it's the North Atlantic Oscillation. But what this does in the winter time is it actually makes it unusually warm in areas like Alaska, the West Coast, and colder. Oftentimes you get these cold blasts from the Arctic that come down, to latitude, 33 sometimes, so that even, the South will get chilling temperatures. And so a lot of times storms will ride across them, and you start getting a lot of snowfall, and you got a lot of sub-zero temperatures. The only good part about this is when this moves, again, like a sine wave, eventually that warm weather will move. That you see on the West Coast will eventually make its way here. But in between, even when it's freezing cold, in the middle of that sine wave, kind of where that if you look at the three arrows in the middle there, that center arrow there, the air is most still at that point. It's bitter cold, but it's still. So you can, it's 5 degrees outside, but it's not windy. That is actually better observing conditions than going outside when it's 40 degrees and you have a 10-mile-an-hour wind. So as long as you bundle up, that's actually a time to take advantage of observing. Next one. So along with the jet stream, we also have, more heat energy. Again, talking about more heat energy, and we're talking about the clash of hot and cold. You start having more extreme storms. For instance, this is a nor'easter, and this nor'easter has a lot of these tight isobars, which means there's a lot of wind rushing into that low pressure system going from east to west. So what does that do? That causes your seeing, if you're looking in astronomical terms, become inhibited. So if you're trying to view Jupiter on a night after a storm has just blown through, you're going to get a really rough image of Jupiter, probably like the one on the right. Taking into account the surface wind, we're to the east of the Appalachians. So we're getting some distortion. If you look at the graphic on the right, we're getting distortion from this airflow rushing over the Appalachians. And by the time it reaches us, you get these eddies near the surface. So that now, let's say this is site B over here. This is us in Montclair. We're trying to see Jupiter through all these eddies with our telescope. And we're not able to use high power or a large telescope because the image is distorted from the turbulence. Next slide. So if you look on the left, this is Pickering scale. This is a crude way of deciphering how bad or good the seeing is. And you look at a slightly defocused star, and all the way on the right, number 10 is perfect seeing. You see tight diffraction rings around this star. And all the way to the left is a night of horrible seeing. It's completely discernible. You can't really tell whatsoever. The graphic on the right will, you have a large aperture telescope on the right and a small aperture telescope on the left. Let's just say hypothetically, this is a nice 12-inch or 16-inch Dobsonian, and this is a good little 4-inch achromatic refractor. Well, that big telescope is trying to look through a column of air 16 inches wide straight through the atmosphere. Same thing with the 4-inch telescope looking through a column of air all the way straight to the atmosphere out into space. But if you have turbulent air, the distorted light waves are going to be amplified with the 16-inch telescope compared to the 4-inch. So on a night of not so good seeing, even though you may not be able to get the same detail you would have with the smaller aperture telescope, you're less affected by seeing, bad seeing, because you're looking through a smaller column of air. So when the seeing is not good, and your goal for that night is double stars and planets and tight objects, perhaps a smaller telescope is better that night than a larger one. The other thing too is to, use a lower power eyepiece. You're still going to see the effects of bad seeing, but you're not looking at it. It won't be as amplified. When you look at it through high power, you're looking at a smaller piece of the sky, and that piece of the sky, the distortion is amplified. Kevin, can you shoot the next slide, please? So here's a picture of Jupiter from Cliff Ashcraft. He said, allow me to use this image. It's just to give you an example, him trying to image Jupiter on a night of pretty good seeing and a night of horrible seeing. So, yeah. So basically, this is almost the same image, the red spot. You can see there's a blob there on the right. That is the red spot. But you can barely make out any detail on the image to the right compared to these two on the left. Next slide. So, Kevin, do you use the mouse? Actually, I can put there. It should be a video.
Oh,
Hit play on there. Thank you. So, this is what Saturn looks like. This is what the effect of bad seeing looks like through camera. Taking video. So this is allowing me to reflect, and I'm going to pose this question to people in the audience. What are your memories from 10 years ago, 15 years ago, viewing planets, compared to, recent times? Visually, I can tell you myself, I was able to use telescopes in 10 inches of aperture or so, over 300 power on quite a few nights. Now, if I get one once a year, I consider myself lucky. Obviously, there's more opportunities than once a year, but I might not be out observing at those times. Nowadays, on average, when I try to look at Jupiter or Saturn, I can maybe get 150 to 200 power if I'm lucky. On those nights, because a lot of times the jet stream is settling out on top of us, and that is what we get to see. Has anyone else had similar experiences?
I have a question.
Yeah, go ahead.
Any software that can stabilize that?
So there, I know ZWO makes an atmospheric dispersion corrector you can put in front of your camera or eyepiece. It is a piece of hardware. So I'm not sure exactly how that works, but that there are, professional observatories have things called adaptive optics, where they will make adjustments. The mirrors are in segments, and they'll make adjustments to the seeing conditions of the night. So
Beyond my budget.
probably beyond our budget. I would look at that atmospheric dispersion corrector. If you ever talk to Cliff Ashcraft, he knows a lot about that. The person that actually sent that image to Jupiter. But if they do exist, that technology might get better as time goes on. But right now, it is the high budget thing. Next slide. So, what about the future of professional astronomy? Observatories Mauna Kea in Hawaii, Chile, BLT, and all those telescopes. It's projected by 2050 as the planet warms. Even at those high altitudes, they're going to start to become affected by more moisture, bad seeing, more turbulent atmosphere, and frankly, the temperature changes that the observatories are not used to, that their own climate control systems were not originally made to handle. So that data, what that means is that scientific data will become degraded because of, not because of the instrument, but because of the conditions around the instrument, above the instrument, so on and so forth. Next slide. So professional astronomy does have a part to play in climate change. This is really the only part I'm going to talk about as far as actual greenhouse gas emissions. NPR report, an article like this a couple of weeks ago, basically said that professional astronomy adds about 20 million metric tons of carbon dioxide a year to the atmosphere. One of the big problems is travel to professional meetings is carbon dioxide heavy, probably mostly from airline traffic, things of that nature. The use of supercomputers gathering the data is also CO2 heavy. The climate control inside the dome to keep the temperature close to outside temperatures. Basically, you have to keep the telescope and the outside temperatures within equilibrium to keep the optics to be cool. The same way you would cool your telescope, they have to do it as well. But the fact that they're inside a dome, they have to cool or heat the dome to do that. Some of the solutions, putting solar farms, most of these areas are high altitude areas anyway. They put solar farms out there to power the climate control system, and also use those same solar farms to help power the supercomputers. They're cutting down on flying to meetings, doing remote meetings, much like we're doing right now. And they're also doing remote observing with the telescope. So they'll, for instance, let's say Mary Lou has telescope time at Kitt Peak. She doesn't have to travel to Kitt Peak anymore. She can log on with her laptop, and by doing so, log into the computer that's there on site and take over that computer. It's what's called remote desktop, RDP, and then control that computer from the comfort of her living room. So this is kind of a new thing, and it beats flying there, and it's saving emissions and greenhouse gases. Next slide. So what are we for lowly amateur astronomers to do in all this? Become more diligent. Don't let a good observing night pass you by if you can help it. Obviously everybody has a plan, but realize that maybe a good night of observing doesn't come around so often anymore, and plans are not necessarily as firm as they would, let's say you have to be somewhere. Maybe you change your plans, and DVR your program that you're going to watch that night, for instance, and go out and observe. You pay attention to apps, download an app like Astrospheric. That's one of my new favorite apps. And old clear dark sky chart. You get that on your computer, you get that on your phone, and you can kind of plan out your observing for the next few days. What does the sky look like? And you can see over here the old blue color, gray color, light blue color. The same blue colors that we saw earlier are in these charts. Don't be afraid of the cold if it's not windy. Bundle up. You'll actually be warmer than you would be if you went out on a windy night and it was, like I said, the difference between going out with a 10-mile-an-hour wind and it's 40 degrees versus 10 degrees and it's no wind. You might find you'll get some good observing in and you'll still feel warm if you bundled up. Electronic assisted astronomy can cut through haze for deep sky objects. So keep that in mind. Obviously, it can't go through clouds, but if it's hazy, you'll be able to still do some observing. Light pollution filter technology is also improved for EAA compared to recent years. You can cut out those pesky blue bands and concentrate a little bit more on the redder hydrogen alpha band. Next slide.
Mark,
Yeah.
you also have those tints you can use to surround yourself.
Right. That will help you with light trespass. Like if this light was, which you see blasting at you, and it will cut the light instead of hitting you in the face. What it won't help with is the light above your head with the actual sky glow and moisture. But that will do something.
Yeah, we're talking about the temperatures and the wind.
Yeah, that can. It absolutely can. It absolutely can. That's a good point. Thank you. So this is an example of, took this screenshot today of the clear sky chart. You can just go to, myclearskychart.org and you find your local area's clear sky chart. And as long as you learn to read, the bluer it is, the better it is. And the grayer it is, the worse it is. So for instance, tonight would not be a good night for seeing. It's light blue, it's below average, right down here. So planets are going to be difficult. Matter of fact, planets may be difficult all the way until Friday. But your cloud cover and your transparency tends to vary. Your cloud cover seems to be okay, but the transparency, that's the moisture in the atmosphere. So you can see that changes through the day. Even though it says you're cloud free, that moisture level is still changing from bad to worse to better. So if you stay on top of that, you can say, I'm looking at this. I say, hey, it looks like Friday night's the best night. Right around 8, 9 o'clock, right in this area here. That's where I would want to do my observing. Because the sky is clear, the transparency is good. And well, okay, if I want to do planets, the seeing's average, but that's about as good as it's going to get for the whole week. Essentially, right in this slot here. If you're looking for deep sky objects, your transparency is the thing you really care about the most. That's what you really care about. Next. So the other thing you could do, if you live here in Montclair, you could get out to a slightly darker sky. You don't have to go travel to the Adirondacks, but if you make a trip, an hour trip to the west in Jenny Jump, you're further away from light pollution. You're also further away from more of a concentration of those blue LED lights. So those two things together will give you a better observing experience, even if you still have to deal with some light pollution. That trip would be worth it. Next. So the other thing, if you really get good, if you become a good astrophotographer, or if you're used to electronic assisted astronomy, or if you're a teacher, or if you're into science, what some folks do is they rent telescope time in some of these remote observatories out west. They call them telescope farms. There's two types of telescope farms. The kind where the telescope is already set up there for you and you go in and you rent some time on it. And maybe you spend $40 for 2-3 hours of telescope time. And that's money well spent. But you have some folks like Omar. Is Omar with us tonight? I'm not sure. But he rents a pier down in Southwest Texas. And he sent his own telescope down there. So that roll-off roof opens up every night that it's clear. It's clear more often there than it is here. And he can go take beautiful images anytime he wants. There's also a lot of other types of telescopes in that large roll-off roof observatory. So it's not just one telescope, it may have like 20 or 30 telescopes. The room could be 3 times the size of a giant, it's a giant roll-off roof. So the roof comes off, telescopes go into action. Some of them do science, some of them do spectroscopy, some of them do asteroid applications, some of them do astrophotography. That can be costly. He spends quite a bit of money just to keep that one thing there. But what often happens, 2 or 3, maybe 4 people, friends or club members, go in on it together and split the cost, and they use that telescope at the same time. And then all of a sudden it becomes affordable. So that is another way to get around this if you become serious. But the former way, just to rent some space for a telescope and a camera that's already there and existing, is a lot more cost effective, and you're not tied to a rental being there all the time. Next slide. So again, main takeaway. Don't waste a good observing night. Be flexible, you know. Which telescope are you gonna take out? Or is the sky, is this transparency good? But the seeing for it, maybe you want to look at galaxies and nebulae and star clusters. Is transparency not so good, but the seeing is good. So you can see Jupiter, but there's a little bit of mist and haze and whatnot. So planets are probably the best thing to observe on a night like that. If you happen to have a night where you're blessed with both conditions, you can, you know, go about your normal observing, but that doesn't happen so often. And the other thing is, you know, travel to a nearby dark sky site. Do not, you know, throw that idea away because maybe that hour trip doesn't sound so hot to you at the moment, but once you get there, you'll be glad you did. But most of all, don't give up. And thank you very much. Any questions? Anybody on Zoom?
Unfortunately, we can't see any of this while we're you know, doing a presentation. We can't see the chat. So I'm not quite sure what that was about, but
Oh, God, okay. Is there anything you want to read from the chat?
not particularly. There was some long message there, which I don't know what that was
Okay.
about. If someone wants to speak up, they can certainly do so.
Okay. Does anyone else on Zoom have questions? Very good.
I have a comment.
Yeah.
The speaker next month will be Terry Zittrich, one of my friends from Vermont. She's going to talk about renting a remote telescope or remote telescope sites and what experience she's had in doing that and how much fun it is.
I'm very curious.
That's awesome.
Yeah,
That's going to be next month
great.
by Zoom.
I,
Totally by Zoom.
well, we know that works.